Good afternoon, everyone. Am I audible to everyone?
Sir.
Today is the lecture number 3 of this heat treatment class, and today's topic is on heat treatment definition, heat treatment steps, the factors which affects the heat treatments, and process variables in heat treatment, and the objectives of heat treatment. Why we do heat treatment. So this topic is a kind of introduction part, and it is obviously a very important topic because before moving into various kinds of heat treatment, you should know the starting part, that is introduction to the heat treatment. So this is now the mechanical properties of engineering materials. What are the different mechanical properties? We know that basically hardness, strength, ductility, toughness, stiffness. These are mechanical properties of the metallic materials basically, or any engineering materials, right? Metallic materials is one of the engineering materials we have. But the question is, mechanical properties of these engineering materials can be altered by. So these are the two ways we can alter the properties of a materials. One is the relative proportion of micro constituents or phase. If we change the proportion, we can change the properties. And another one is the change in density of the defects or number of defects. Already we have discussed that, but you understand the thing, right? But now, how these above can be changed? How we can change the relative proportion of microconstituents, or how we can change the density of defects? So the main technique is by a technique or a process known as heat treatment. So heat treatment is a process which can modify the relative proportion of microconstituents, or it can modify the number of defects. Defects means dislocations or grain boundaries, like that. Now, what is the definition of heat treatment? So, heat treatment can be defined in a way. It is a process of heating, holding, and cooling of metals, alloys, so as to get desired properties. So that means the heat treatment involves heating, it involves holding, and it involves cooling the metals, right? And now the question is, what exactly does in heat treatment? Heat treatment, what we basically do. So what we do, we have some steps in the heat treatments. You can see these are the steps. The first step is heating to a predetermined temperature. That means what we do, we take the metal or we take the alloy to a particular temperature by putting it inside the furnace. Then what we do, what the next step, we have to do holding. This that
Sir,
means
sir, can
yes.
you allow Abhay to join?
Again, I am requesting please join in time. Hmm. Everybody, please join in time so that I will not get disturbed during the lecture. The second step is what? Holding. That means after reaching to that particular temperature, you have to keep the sample for a particular duration. That's the holding cycle. So holding in technical it is called soaking also. SOAKING. Then what is the step number 3? The step number 3 is what? We have to do cooling the sample finally. After holding, we have to do cooling the sample. Cooling the sample basically to the room temperature, or sometimes below the room temperature, depending upon our requirement. And it should be at a desired cooling rate. Cooling rate should be desired. That means it may be slow, it may be fast, it may be very fast, like that.
Excuse
And
me, sir. Mohammed wants to join.
ହଁ ହଁ ମ୍ୟାମ୍ ସରି ମୁଁ ଏକ୍ଚୁଆଲି ନେଟଟେକ୍ ଗୋଟେ ଛାଡ଼ିଥିଲି ଯେ ଆପଣଙ୍କର ସେଇଟା ମେଟେରିଆଲ ଅଠର ଥ୍ୟୁରି ଆଉ ନଅଟା ସିସ୍ମିକ୍ ଠିକ୍ ଅଛି ନା ମୁଁ ମେଜର ଆଇ ଏମ୍ ନଟ୍
again, I am requesting everybody to join in time from the next class. It's not like that after sending you the link, you are joining after 15 minutes. And these steps can be repeated depending upon the requirements. Each step is carried out in solid state. This is important. So whenever you are doing heat treatment of any materials, basically steels or aluminiums or any alloys, you should this should be taken in care that there should not be any melting. So the heat treatment is always carried out in the solid state. There should not be melting of the material, right? So best example I am give you right now I can give you is the one heat treatment in the final fabrication process such as deep drawing operation is annealing. So annealing is a heat treatment which is given in between the deep drawing process. Deep drawing process means we are drawing the materials to a large extent. That means a severe plastic deformation is happening in the material. That is a deep drawing process. So you understand in case of deep drawing means basically it is a cold working process. Cold working process, you understand, that is done below the recrystallization temperature. So during cold working process, what happens? A lot of dislocations generates inside the material that leads to strain hardening effect. So to reduce the strain hardening effect, so that we can deform it more and more. So we have to do a heat treatment in between them. That is annealing heat treatment. So by doing annealing heat treatment, you can draw it further. You can deform it again to a large extent, right?
Sir,
Yes.
sir, during the deformation annealing is done or after that?
Yeah, this is a very nice question. Obviously, you suppose you do deep drawing first. You have deformed the material to a large extent, but again, you haven't reached to the particular shape. Your desired shape is not reached right now after doing first deep drawing. So what you need to do? You need to do again deep drawing, right? To reach to the final step or to reach to the desired shape, right? So you cannot draw it. Why? Obviously due to strain hardening effect, because it is a cold working process. So what you need to do? You need to do annealing. So once you do annealing process, you understand what are the steps. Recovery, recrystallization, grain growth will be there. So again you can draw it after that. Again after drawing it, again it will become strain hardened. So you cannot draw it. So finally, suppose after doing deep drawing, again you have to do annealing process. Fine. So that means obviously the point here is annealing will bring ductility in the material so that you can draw it further. Yeah, you have any doubt?
No, sir, no.
You understood the point?
Yes, sir.
Okay. So what are the requirements for heat treatment? Suppose you want to do heat treatment of a steel. So what you require? Obviously, you require a furnace. You can see a figure. You require the desired sample. So this is the steel sample. You require a furnace. Furnace is required to, because furnace we can rise the temperature. So it's a furnace is required. We require a sample. We require a tongue to hold the sample for our safety issue, and we require some gloves. And we sometimes require some quenching medium if we desired for faster cooling rate from the high temperature. We required a desired cooling rate, so we required tanks. So you can see this is a cooling medium, quenching medium. It may be water, it may be oil, it may be some brine solution or some synthetic coolants. We require that. So you can see quenching is done here, right? So these are the requirements. The main requirement is the furnace and the sample, tongue and gloves. But sometimes when it is required to do quenching, very fast rate of cooling, we require a quenching tank containing quenchant. This is called quenchant or cooling medium or quenching medium. Now, typical heat treatment cycle. So as I told, heat treatments involves 3 cycles. The first cycle is called heating cycle, where what is heating cycle? Heating cycle means I'll show you soon. Second cycle is soaking cycle or holding cycle, and final step is the cooling cycle. This can be repeated. Again, you can do heating, soaking, and cooling. But this is a generalized heat treatment cycle, which is shown in a graph. You can see this is this axis is the temperature axis in degrees centigrade, and this is the time. It may be hour, it may be seconds, it may be minutes, like that. So you can say this is the heating cycle. Up to this, it is heating cycle, and this is holding cycle. Holding cycle, you understand, is the time axis. From here, this point to this point, this is the holding time. After reaching to that particular temperature, holding time is decided or the soaking time is decided, right? Then finally, after when the soaking time is over, you have to cool it. The cooling may be, this is a slow cooling. You can do cooling like this. You can do cooling like this, directly from here to here. This will be a quenching, but this is a slow cooling. So this is heating cycle, this is soaking cycle, and this is cooling cycle. Fine.
Sir, will the rate of cooling affect by anything?
Yes, obviously. I'll tell that soon. Just wait, huh? I'm going to discuss that soon.
Sir, some students are trying to join.
up to 2.5 to 5 lakh जे 5% देले से तार एटा होची माने देखंतु 2.5 रु 12500 तापने पुनी 5 केते 5 to 10 5 to 10 केते 20%.
Again, I am repeating. Please join. Please do not join after the required time. Right? You should join in time. The moment I am giving you the link, you should join within at least 10 minutes. 10 minutes is enough to join.
Sir, what is that mention above this holding graph?
Which one? This one?
620.
This line. You are talking about this line?
No,
Yeah.
no, sir.
This one.
Yeah, that's one.
That's one. It is written 620 degrees centigrade. 620 degrees centigrade plus minus 20 degrees centigrade. Per hour. It is degrees centigrade per hour.
Per hour means it is a
Per hour. Actually, this is only time. This is degree centigrade per hour. This is maybe there is a mistake. I have taken from internet. This image I have taken from internet. This is not my own image. So you understand? I will tell you. Just wait. No need to worry about that. I will tell you soon. What is that exactly? Again, just look at some other heat treatment cycles. You can see this is the heating cycle. Up to this. Then this is the holding cycle from here to here. That means after reaching the required temperature, you have to hold the sample or you have to soak the sample. Then after soaking or holding, here we are doing quenching. This is the cooling cycle. You can see the cooling cycle is very fast. The cooling rate is very fast. After reaching at this temperature, so this is the room temperature. You just imagine this is the room temperature or just above the room temperature, like 50 degrees centigrade, like that. Again, we can give heating. Again, I'm doing this heating cycle again. Then this is the holding cycle or soaking cycle. And finally, this is the cooling cycle. So you can see the difference. Here, the cooling rate is very fast, but here the cooling rate is slow. You understand how? This is the time axis. From this time to this time, the cooling is happening very slowly. But here, cooling is directly occurring. There is no time. You are not giving any time for cooling, right? Because this is a straight line. Again, same. Okay. Again, same thing. It is here only, but here it is written artificial aging. This solution aging. This is quenching. This is artificial aging. Do you have any idea of what is this kind of cycle is showing? Okay, do you have any idea about precipitation strengthening? I think I have taught you in physical metallurgy or you have studied somewhere else about some precipitation strengthening or precipitation hardening.
Yes, sir.
In which topic you have studied apart from physical metallurgy?
Sir, you only taught in physical metallurgy, no?
Okay, fine. Very good. You have remembered that. That is very good. You have remembered that. So precipitation strengthening, if you remember, in precipitation, what? We have a matrix and we have some precipitates. Precipitates are actually not soluble in the matrix. Actually, what happens? Precipitates are basically carbides, nitrites, carbonitrites, or some intermetallic phases. So phases between two metals, like that. So what happens actually? How we do precipitation in a materials? This is the heat treatment cycle. So you have to remember, if somebody will ask to draw a heat treatment cycle for precipitation strengthening material or for a precipitation strengthening alloy, so this is the heat treatment cycle, right? Sometimes in interview they ask, please draw a heat treatment cycle for precipitation strengthening alloy or precipitation hardening alloy. So this is the diagram. Either you draw this diagram. This is actually for a steel. This diagram is for a steel. Why? Can anybody tell me why this is for a steel? Precipitation strengthening alloy, steel alloy.
So A3 and
Oh,
A1
very
can
good.
be
But you are looking at A3 and A1. Yes, very good. Well, do you remember? Anybody remember what is A1 and A3?
Critical
Sir,
temperature.
A1
Critical
is
temperature. Very good.
7.6
Critical
days.
temperatures. Well, what is the name of this A1? Which critical temperature? And what is the name of this one?
727A1.
Very good. 727 A1. That is actually called lower critical temperature. Remember, in heat treatment, we use these terms: lower critical temperature. A1, or it is sometimes called AE1. Do you remember what is E represent? AE. You can write A1 or AE1. AE represent the equilibrium. If you are writing AE, that is equilibrium. Similarly, you can write AE3. So that means if it is a lower critical temperature, what is this then? 3.
The
Upper critical temperatures. Very good. Critical temperature means lower critical.
Austenite reason.
Can you tell me which steel?
Hypo.
Check.
The metallic detector.
Right. Is required.
Martensite.
Martensite will form, but
Substitutional solution.
sorry, can you
Substitutional solution.
substitutional or supersaturated solid solution? It is supersaturated, not substitution. Supersaturated solid solution. Why supersaturated? Because during quenching there will be no diffusion. You understood now? If you do slow cooling, then diffusion will take place. Carbon will come out, the austenite. But you are not giving any time. The composition of austenite is same as the composition of this phase which will form. There is no diffusion here. That is why it is a supersaturated. Because you understand, solubility decreases with decrease in temperature, yes or no? Solubility increases with increasing the temperature. Here temperature is very high and you are reducing the temperature. Solubility will decrease obviously. You are not giving much time. Which kind of solid solution is a supersaturated solid solution? So upon quenching, we are forming a supersaturated solid solution. That means even after at low temperature, all the substances are in soluble form, austenite phase. So after that, our aim is to get precipitates. How to get precipitates? You have to do this kind of heat. Again, you have to heat. This one. Again, you have to heat, but this heating should be a moderate temperature. When you can anybody tell me why heating to a moderate temperature, the precipitate? Which kind of phenomena will start?
Diffusion.
Diffusion. Obviously, diffusion will start. But here, what we are not doing? We are not going above this temperature, A3. That means we have to do collisionizing below what? Which?
A1.
Sorry, we have to do edging or below A1. A1, you have to hold it. Some particles will come out that will form a to do to a moderate temperature. Slow rate. Rate. Here, after this, precipitates will form. You have a matrix and you have a you people have seen the kind of aluminum you have seen. You please go through that. Huh? I will show you. Now we'll discuss about heat treatment objective. So what is our objective? The grain move any rest. Sometimes what happens? Decrystallization working material. Sometimes we want to the case composition. These are the things. There is a question. Sometimes, suppose you do heat treatment on old significant effect on the property will significant. Can you tell me why? People guess. You do heat treatment on copper. Heat treatment. Means the physical mechanical property. This one. Still will show a change in the property. I can give you.
What is a single phase?
Yes, if you heat the copper to a high temperature,
8 gets
Yes.
transformed to alpha,
Yes.
beta, gamma.
transforms into various phases. You understand different phases? What? Different
Mechanical properties.
properties. Already I have taught you in the previous lecture. If you different phases have different properties. If ferrite will form, it is very soft. Perlite will form, it will be tougher and stronger. Martensite will form, it will be more harder and more strong. Austenite will be there, then it will be soft. So you understand why there is a significant change in properties if you give heat treatment? What is the conclusion? What is the conclusion here? Can anybody tell me in one line what is the conclusion? Can you people tell me the conclusion? What is the conclusion I can say? Why steel will show a change in property on heat treatment, but copper will show some properties, but it is not significant?
So because with the change in temperature, copper doesn't change its phase, whereas the steel changes its phase.
Yes, because steel is nothing but it is iron, right? It is an alloy of iron. Iron always show allotropic transformations or allotropic modifications. You understand? So due to change in the phases or due to change in the structures, the property gets changed. Okay, fine. This is over. Then factors which needs to be taken care of during heat treatment. Factors which needs to be, okay, fine. Somebody have asked me about the significance of, okay, process variable. I'll tell you that. Yes. Factors which need to be taken care of during heat treatment. So these are the factors which need to be taken care of. One is predetermined temperature, holding time, soaking time or soaking duration, cooling rate, and atmosphere surrounding the sample during heat treatment. These are the factors we need to take care of, right? Predetermined temperature. The first one is predetermined temperature. Predetermined temperature means up to what temperature we have to take our sample from the room temperature. Basically, we are taking the sample to above A3, right? Suppose can anybody tell me if you have a eutectoid steel, so at what temperature we need to take it? Tell me. What will be our predetermined temperature?
A3.
A3? Listen to the question carefully. You have an eutectoid steel.
A1.
Will be the A1 or just above A1?
Just above
Just
A1.
above
Just
A1.
above A1. Why can you just above A1?
Sir,
Because at 0.8%
above
of
A1,
carbon,
martensite is there.
Martensite will be there? What you are saying?
Austenite.
Austenite. Sorry.
Austenite will be there.
Austenite, yes. Because you can see that this is a very good image. Look at here. This is which kind of diagram? What is this diagram?
Phase diagram, iron carbon.
Phase diagram.
Iron carbon phase diagram or iron cementite metastable phase diagram. But this is okay. See, just look at This portion. What is this portion showing?
Austenite.
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 Yes, this shaded portion is austenite. That means just you have to remember during our heat treatment, in maximum heat treatment, our starting temperature is the austenitizing. That means from the room temperature, we have to take the steel, the austenitizing temperature. This is our priority. Do you understand why? Why we have to austenitize the sample?
It is a single phase.
That is a single phase. Very good. That is a single phase. Everything will be get soluble in that phase. But what is the interesting part?
Solution aging.
No. The interesting part is this is a
This is
single phase.
larger area of the.
It's a larger area, but is single phase. But I told you this is always a parent phase. Phase transformation starts from here when you do cooling. Right?
Yes,
The
sir.
parent phase, no? Always phase transformation starts from here. This phase can transform into ferrite. This phase can transform into perlite. This phase can transform into benite. This phase can transform into martensite. Right? So this is a starting phase always. Parent phase. So everything should be soluble here first. So you can see this line is which line? This line is which line?
A1. A1.
This is A1. This is a lower critical temperature, A1 or eutectoid temperature. Composition is eutectoid composition, this one. That means determined temperature will be above
A1.
Above A1, from just above this temperature here, for example. To heat, that means predetermined temperature is here. You have to heat the steel from here to this temperature only. But if you have a hypoeutectoid steel, then what is this line?
A2 line.
A3.
The A3
A3
line. And what is this line?
ACM.
ACM.
ACM. Right? So if you have a 0.5% carbon steel, then you have to go above which temperature?
A3.
A3 temperature, right? Suppose you by mistakenly keep the steel between A1 and A3. What will happen? Here you are doing heating here for a 0.58% carbon. What will happen? Hold the steel if this predetermined temperature is here.
Austenite plus ferrite.
Yeah, here austenite plus ferrite will be there. You are doing cooling. So what will happen? And
Eutectoid ferrite and perlite will form.
the problem will be what? The problem will be ferrite which will be here will not get transformed, right? Remain as ferrite. But here austenite which will be there, that will transform into again in which phases? It will transform into
Perlite.
perlite. Very good. That means more amount of ferrite will be there. Perlite will be also having ferrite, and initial ferrite will be also initial ferrite. More ferrite will be there. So what is the property of steel now? It will be deteriorate. Strength will be what? Decrease or increase? Strength will be decreased or increased? Decreased, obviously. Why decreased? Because due to more proportion of ferrites. You understood now? But if you heat the steel above A3 here and you are doing cooling, then what will be the phase formed? From this temperature to here, room temperature. You'll get?
Perlite.
You'll get perlite and some proectectoid phase. The amount of proectectoid phase will be less upon the composition. Anyways, understood? So here, first is the predetermined temperature. Predetermined temperature means already you have an idea that I have to the steel to this particular temperature. Your predetermined. I'll tell you how it is affected. Holding duration. Holding duration, soaking duration is also to understand. Means up to what interval of time you have to hold the steel at that particular predetermined. One is the cooling rate. Cooling rate means at what rate you are cooling, at a very fast rate or very slow rate, or you are doing. Atmosphere also affected. Not happen. It is affected because if it is a normal atmosphere, corrode the sample. Sample will get corroded. It will get oxidized. There is a loss of material. Because due to formation of a oxide scale. Oxide scale will form. The loss of material will get removed. Yield will be less. So you can coat it. We are giving some coating, or you can control the atmosphere. some nitrogen atmosphere, some can use some argon atmosphere, depending on, but that will be expensive. So nitrogen and argon provide inert atmosphere. If you use a normal atmosphere, because oxygen will be process variable in heat treatment. So what are the process variables? So these are the process variables: heat treatment temperature, rate, cooling time, and are all the process variables. Means to what temperature we have to heat the sample, heating the sample at what heating rate. Similarly, if you're what is the holding time, less time or more time, cooling rate. These are the process variables. Now this is important. But you have asked me question, I will explain. These process variables are affected by composition, size and shape, final properties required. But you have asked me cooling rate. So just you have to remember, it is the predetermined temperature. To what temperature you have to take? Can anybody tell me? Just few minutes. The predetermined temperature. How you will decide? Tell me.
By seeing the composition.
Composition. Can you just?
Sir, if that is eutectoid, then we have to just go to the 727, and if it is 0.5, then we have to go to
7 or just above 720?
just above.
Just above 720. It is an eutectoid steel. You have to just go above A1, the predetermined temperature. Next.
If it is 0.5, then we have to go to that A3 line where
A3. But just one point I would like to mention, but if you have a steel above eutectoid, never go above A6. That is why I will tell you later. You can write it down if you want. For an hyper eutectoid steel with more than 0.8 weight percentage of carbon, we never go above AC3. But generally, go above AC3. We are not going above AC3. We are doing heat treatment in between A1 and AC3. Why? I will tell you later. Always for hypoeutectoid steel, we have to go above AE3, upper critical temperature. Fine, you understand this one? Size and shape. Properties. Size and shape I will tell you later here. Now the question is final properties. Okay. Can anybody correlate cooling rate with final properties? Before I told you the initial phase and final phases. Initial microstructure and final microstructure. Can you correlate that one with cooling rate?
Yes, sir.
Yes.
From the triple T diagram, we can see it. Like rapid quenching, if we do, we get martensite.
Very good.
When we do slow, a little bit slow cooling, we get benite. So microstructure alters, so the property also changes.
Yes. What about perlite? You haven't taken
Perlite more slower than benite.
more slower than, very good. But what about two types of perlites?
Sir,
Coarse perlite and fine perlite.
the slowest one will course, and
Yes, very good. If you do very slow cooling, very slow cooling, you will get a coarse perlite. Fast cooling, you will get a fine perlite. But you will change. Similarly, if you do quenching like this, get martensite. All different phases have different properties. They have shown you in previous lecture. That means you understand cooling, how cooling rate affects the final property. According to our final property, go fast, very fast. These are the process variables. Okay, for about holding time, size and shape is important. Related to this, time will be decided by size. Suppose your size will be bigger, time will be more or less. The size of the sample is bigger, or the section cross sectional thickness is more. Holding time will be less or more?
More.
Obviously more. Can anybody justify why more?
We give 1 hour of holding time for 1 inch of thickness.
Yeah, you know that. I understand. You have you are doing a project. I know that's why you know. But why more holding time is required? Tell me. If the cross section thickness is more, you have to remember. Thickness is important. The length is not important. The breadth is not important, but thickness is important. Higher is the cross sectional thickness, higher is the holding time. Lower is the cross sectional thickness, lower is the holding time. Why? Because
For every
just
for
look at this
complete
one.
conversion for complete conversion to
Yes, for
STL.
complete conversion to what?
Also, there was a unit.
For complete conversion of?
Austenite thickness.
Yes. You have to completely austenitize the sample. If you give a less interval of holding time, what will happen? Surface will get austenitized. But what about the inside part, core part? What will be the core part? The core part will be not in austenitizing temperature right now. Understood now? To completely austenitize the surface as well as the core to give sufficient time. Time is more. And also, another important point is composition also affects. Suppose you are dealing with a high carbon steel, high alloy steel. Can anybody justify? High holding time will be more. I told you just before. Call it. If you are dealing with a alloy steel, suppose you are dealing with niobium, vanadium steels, holding time will be more. In that case, compared to a plain carbon steel.
For diffusion to take place.
Diffusion to take place. But what kind of diffusion? Just remember this image. You recall this one. Solutionizing. I told you when I am talking about solutionizing process. Because I told you, because niobium carbides and more time. Diffusion of these particles are very easy. You had more time. You are dealing with an alloy steel, niobium steel, tungsten also form by not easily. They need more time to. Now you people understand. And the important point is they sometimes The important point you have to.
Sir, 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 ଆମେ ହିଟିଂ ସାଇକେଲ ଯେମିତି soaking time ଦଉଛୁ ଟ୍ରାନ୍ସଫର୍ମେସନ କମ୍ପ୍ଲିଟ ପାଇଁ ସର ଆମେ ଯଦି କୁଲିଂ ଟାଇମ ରେ ଯେତେବେଳେ ମାର୍ଟେନସାଇଟ୍ ଫର୍ମ କରୁଛୁ ସେତେବେଳେ ତ ଖାଲି ସରଫେସ ରେ ମାର୍ଟେନସାଇଟ୍ ଭିତରେ କମ୍ପ୍ଲିଟ ଟ୍ରାନ୍ସଫର୍ମେସନ ହଉନଥିବ ସେମିତି ବି ହଉଥିବ.
Yes, very good question. Very good question. I will tell you that. That is actually we do an experiment called. Experiment name is Jomini and Quench test. I will tell you that in that part. Yes, that happens sometimes. That's why if you do slow cooling, this will become the surface will become martensite, but that part will not become martensite. That's why we are doing fast. Fast cooling can give you maximum chance forming martensite throughout the cross section. That's why there is a term called hardenability. Anybody have remember the hardenability term? IPM also I told you sometime. IPM. Hardenability. No. Hardenability. What is the difference between hardness and hardenability? That's why I have told you to go through the IPM. Or at least I taught you. Hardenability means easy to form martensite throughout the entire cross section of the material. How easily you can form martensite throughout the cross section? It's called hardenability. But hardness is the resistance to plastic deformation, which is measured by indentation method. Just please go through the tensile test part. Okay, fine. You understood now. And the important point is sometimes what happens, cementite particles get easily soluble at above like above 650 degrees centigrade. It will start getting soluble into the austenite matrix. But what about the niobium carbide, vanadium carbide? They are not get soluble. They need some high temperature. Like they need some temperature of around 1050 degrees centigrade, above 1050 degrees centigrade, or above 1100 degrees centigrade. Right? So in that case, sometimes we need high predetermined temperature. So you people have understood how they are related with one another. You can write it in your examination, right? So this is okay. This is okay now. Okay, fine. There is a very interesting concept. Why two furnaces is required sometimes for heat treatment? So a single heat treatment furnace is enough to do heat treatment, but sometimes we need two different furnaces. Why? The reason is what? Sometimes what happens. Okay, before telling that, let me tell you one important. Predetermined temperature is sometimes inversely proportional to holding time or soaking time. Right? Okay, there is a confusion. Actually, predetermined temperature is fixed. Actually fixed it is. It is not variable, right? But the time of holding, time of predetermined temperature sometimes changes. It is sometimes inversely proportional. If you are holding the sample for more interval of time, the predetermined temperature may be somewhat lower. But if you are doing less holding time, you can go for a higher temperature of the predetermined temperature. You people understood why this is so? I will tell you soon. But question is now why two furnaces are essential sometimes. So two furnaces are essential because of few reasons. The first reason is we can prevent the oxidation of the sample. We can prevent the oxidation of the sample. As I told, if you keep, because heat treatment is a high temperature process, high temperature oxidation will be there, corrosion will be there. So to prevent the oxidations of the alloying elements or some particular principal alloying elements, we have to use two different furnaces for heat treatment. And second point is to prevent the grain coarsening. We do not want our grain to coarsen. If the grain will become coarsen, properties will be deteriorates. The coarser grain will give you more ductility but less strength. So to prevent grain coarsening, to prevent the oxidation of the steels, alloy steels basically, we have to use two different furnaces. Another important point is what? Sometimes get a homogeneous, okay, I will tell you that later. So these are the two important points. So how that can be justified? How that can be justified? That can be justified because can read here. I think I have written here. Which material? Okay, I'll write it over here otherwise. What I have written, preheating and heat treatment temperature. Can anybody think of this one? What is the meaning of preheating and what is the meaning of this heat treatment temperature? Can you people tell me by reading this one, for what is the need, how you can prevent the oxidations, corrosion, or how you can prevent the grain coarsening by using two furnaces? Let me see who can answer. Now tell me, just I have written everything. Can you people tell me how can prevent the grain coarsening or we can prevent the oxidation of steels, alloy steels by using two furnaces?
सर हम जति के अधिक टेम्परेचर जाय जिबा ग्रेन सेते कोर्सर हे जिवो.
Okay, very good. Yes.
तो सेत पे हम जो टेम्परेचर डिटरमाइन करथो प्री डिटरमाइन टेम्परेचर तार बिलो रे जति करबा हम होल्डिंग टाइम टा बढ़ी जिवो. बट किंतु ହେଇଯିବ ଅଷ୍ଟନାଇଜ ମାନେ ପୁରା ଅଷ୍ଟନାଇଜିଂ ହେଇଯିବ କିମ୍ବା ଯୋଉ ଟ୍ରିଟମେଣ୍ଟ ହେଇଯିବ।
Anybody want to say anything?
So the
May I apply?
temperature difference from
Mhm.
preheat to the heat treatment temperature is low.
Okay, let
I
me
mean,
tell you some important point. When you are rising the temperature of a furnace, what happens? Initially, the temperature will rise at a very fast rate. Then after a particular moderate temperature, it rises at a very slow rate. You understood my point? Suppose from room temperature to 400 degrees centigrade or 500 degrees centigrade, the temperature rise will be very fast. But after 500 degrees centigrade, the temperature rise 500 to suppose 900 degrees centigrade, it will become very slow. Slowly it will rise. What will happen? Actually, in the heat treatment, what basically we do, we take the sample and we put it inside the furnace, then we switch off the furnace. Now, can you correlate this one? What will happen? What will happen to the grain?
Sir, again.
During the heat treatment process, we take the sample, then we put it inside the furnace, then we switch on the furnace. Then the furnace temperature will rise, and finally it will reach to a predetermined temperature, and finally we give some holding time, then finally we take out the sample, or we keep the sample and switch off the furnace. This is the way we do heat treatment. So how we can prevent the grain coarsening? Just tell me. By using two furnace.
सर गोटे फर्नेस जेतल टेम्परेचर राइज हे जाय हला परे तापर जे सैंपल हम रखिया था
Then if you do that, sometimes what happens, it will generate some cracks, thermal shock. Understood the point?
Yes, sir.
Thermal shock will be there and it will generate, because there is a sudden temperature gradient will be created. So that it will lead to thermal shocks. It can generate some defects, cracks in the material. So do not do that, basically. This is very simple. Just imagine you have two furnaces. Suppose your predetermined temperature is 950 degrees centigrade or 1000 degrees centigrade, right? So you do what? In the first furnace, you keep a temperature of suppose 500 degrees centigrade. In the second furnace, you keep the temperature at 1000 degrees centigrade, right? Or what you do, you take the sample and put it inside the first furnace and you switch on the furnace. The temperature will slowly rise from room temperature to 500 degrees centigrade. It will take some time. But after reaching at 500 degrees centigrade, you take out the sample and you put it into the another furnace, which is already there at 1000 degrees centigrade. You understood the point now? So what will happen? We are reducing the time. From 500 to 1000 degrees centigrade, the time is required. We are reducing that time particularly by just taking out the sample from at a 500 degrees centigrade to directly I am putting the sample into the furnace with 1000 degrees centigrade. So we are reducing the time of holding. So if the time of holding will be reduced, what will happen? The grain will be not get coarser. You understood my point?
Yes, sir.
How the grain become coarser? Due to diffusion. More is the holding time at high temperature, more is the diffusion, and more is the diffusion, more is the grain coarsening. You people have understood right now?
Yes, sir.
So that means if we are using two different furnaces for heat treatment, we can minimize the holding time at high temperature. We are minimizing the holding time at high temperature. Since the holding time is minimized at the high temperature, so obviously grain will not become coarser and the sample will become not oxidized, because at high temperature, more is the oxidation, more is the corrosion. Fine. I think you people have understood. Okay, anyways. Now the question is, which material must give slow cooling during heating cycle? Sometimes we can have a slow cooling of the sample. Slowly the sample should be heated in some conditions. So what are the conditions? If we have a large size object, if we have a complicated shapes, if we have sharp corners objects and object with variable cross sections, in that case, we have to do heating at a very, very slow rate. That means starting from the room temperature to the predetermined temperature, the heating should be very, very slow if the situation is like this. And for high carbon steels and austenitic stainless steels. Can anybody tell me why, if there is a large object, why the heating rate should be slow? Just imagine you have a very large object. That means thickness of the object is very more and you are heating at a very fast rate. What will happen?
So the core will not go complete conversion.
No. Just listen. It question is why slow hitting rate is required for a large size object. That is the
So
question.
slow hitting rate.
Okay. Sorry. Let me move to this one. Actually, this is I have written. It is slow hitting, slow cooling, and heating also, and heating. Slow cooling and slow heating. Actually, I'm talking about heating right now. Why heating rate should be slow for large size object? Obviously, because if the size of the object is very large, cross-sectional area is very big, suppose for example. So what will happen? Thermal gradient will generate. That means the surface will get easily reach to the austenitizing temperature, but the core cannot reach to the austenitizing temperature for fast rate. Right? So what will happen? A thermal gradient will generate from the surface to the center. So it will lead to generation of stresses in the material. So stress will generate inside the material, right? That is the one of the reason. But if you do slow heating, what will happen? If slow heating will be, that means slowly the sample will get heat and there will be no thermal gradient. There will be no thermal gradient means there will be no thermal stresses generated inside the material. So to prevent the stresses, we need to do slow heating of the sample, big size sample. But if it is a very thin section, cross-sectional area is very thin, you can heat it at a very fast rate. There is no problem, right? Then complicated shape, can anybody tell me why complicated shape should be heated? Same reason, right? Similarly, sharp corner, that is again same thing. Again, what happens if the object has variable cross-section? If an object have a variable cross-section, that means in some particular cross-section it is very thinner and some particular cross-section is very thicker. So what will happen? Slow heating is required. Why slow heating is required? Because the cross-sectional area which is very thinner, that will easily reach to the austenitizing temperature at a very fast rate. But what about the thicker cross-section? The surface will get austenitized, but inside the core will be not get austenitized. It will take some time. The thermal stresses will generate again. Same problem, And austenitic stainless steel have a very poor thermal conductivity. The heat cannot be transferred easily from the center to the core. So that's why this is the reason. Similarly, same thing happened to the high carbon steels. So what is the advantage of slow heating of the steel? One advantage is more homogeneous structure. We can prevent what? We can prevent stresses due to thermal stresses, or you can write, we can prevent stress inside the material, and actually residual stress or more homogeneous structure, we can prevent stress. We can minimize the holding at high temperature. Holding time. Right? If you are doing very slow rate of heating, then holding time at high temperature can be minimized. Right? As I told, predetermined temperature and holding time is somewhat inversely proportional. Right? What is the common? So finally, what is the common predetermined temperature for a steel? For a steel, who can answer? What is the common predetermined temperature for a steel?
Austenitizing temperature.
Austenitizing temperature, very good. I have written something here. What is this? Why minimum grain size? Can anybody justify? Just read this one. Common pretreatment temperature for steel is austenitizing temperature. Temperature at which entire sample is austenitized with minimum grain size. Why? Just look at this image. Okay. Just look at this image. Austenitizing temperature starts from here to end over here. So now can you justify that?
Sir, we just go just above that line.
Yes,
not-
very good. We have to go just above the austenitizing temperature. That means you suppose for a eutectoid steel, you can go up to this temperature, 40 degree or 50 degree above austenitizing temperature. But suppose you are going 100 or 200 degree above austenitizing temperature, suppose here. So what will happen? If you're going here,
The grain became coarser.
the austenitized grain, austenite grain will be coarser. So if austenite grain will be coarser, what will happen to the final product? What will happen to the final
coarser grain.
You will end up with coarser products. Final products will be also of coarser size, right? Because austenite will transform into final product only. So bigger coarser grain will finally convert into small coarser final products, right? So that is why. I think you people have understood. Very good. But it is not, so you have to remember, it is not like that you have to go 10 degree above austenitizing temperature. That means there might be a incomplete homogeneous austenite form, right? Austenite cannot be homogenized just above the austenitizing temperature. You have to go like 40 to 50 degree or above 50 degree, not like above 100 degree or 200 degree, right? This is the point. Next one is, now main objective of predetermined temperature, fine grain and homogeneous austenite. This is the main objective. The grain should be fine grain and it should be homogeneous austenite grain. Then holding time, you have to remember the holding time, as somebody told, holding in industry we give holding time of 1 hour for 1 inch, 1 hour plus minus 10 minutes, 1 hour plus minus 10 minutes for 1 inch thickness of the material, or you can say 2 to 3 per mm section thickness, 2 to 3 minute, 2 to 3 minute. So for one, if you have a cross-sectional area of 1 mm, so you have to keep it for 3 minutes. Holding time is 3 minutes, right? And for variable sections, what is the holding time? It depends upon the okay, fine. Can anybody tell me if you have a plain carbon steel and you have a variable cross-sectional area, so what is the holding time then? Do you think that it will be 3 minutes for 1 mm?
The highest cross section will decide.
Very good. The highest cross-sectional area will be decided, right? Suppose at a particular area it is 5 mm and at a particular area it is 1 mm cross-sectional thickness. So we will decide on the basis of 5 mm cross-sectional area. So 5 into 3, 15 minutes. You have to keep it for 15 minutes. Now cooling rate, depending upon what kind of microstructure is needed, that is equilibrium or non-equilibrium. Right? You understand? Suppose you need Udman-Stratton ferrite, or you need martensite, or you need benite, then you have to do very fast rate of cooling, basically. But if you need equilibrium microstructure like perlite and ferrite, then you can go for slow cooling. Okay, so I'll end this topic over here. You can see this is a very good figure. Application of steels. Since in this topic, in this subject, we basically deals with the heat treatment of steel. So basically, that's why I have shown you the application of the steels. You can see steel is a versatile material. Steel have a lot of application. Wherever you'll go, you'll find steel. You can see car, buildings, bridges, ship, this fork and forks, right? This washing machine, railway tracks, the heavy equipments, mineral processing equipment or any transportation equipments. You can see this one, the mill, windmill, aeroplanes, aircrafts like pin, paper clip, clip. So everywhere we have steels, right? and the steels required heat treatments. So that's why we'll study about the heat treatment of steels in the coming lecture. Okay, I think there is no doubt up to this. If you have any doubt, you can ask me right now.